This is a 3 minutes ago one, yeah?
I guess so.
Literally. In this edition of Algebra Workout, we're going to look at linear transformations and how to work with them algebraically.
And as is almost always true in mathematics, it's pictures, at least mental pictures, that will be the key to competently handling the algebra.
The first type of transformation we'll be looking at will be rotations. Now here's a first transformation showing the rotation anti-clockwise through pi by 2 of the unit square. Now I've labelled it F just to help us see the way in which the square has been rotated. To start with, the vertices of the square are 0, 0, 1, 0, 1, 1 and 0, 1. And after the rotation, they become 0, 0, 0, 1, negative 1, 1 and negative 1, 0. Now the second linear transformation we're going to look at is the reflection in the y-axis. So I can show you this with a mirror. Well, that's the reflection. And if I put that in, you can see there it is. Now that transforms the square so that this time these vertices become these. A third transformation we're going to be looking at will be a scaling. Now for this I need two diagrams, a before and an after, because the figures would be on top of each other. Now the before is called the domain and the after is called the codomain. Now in this case, for example, the scaling of a half in the x direction and 2 in the y direction transforms this square so that it becomes tall and thin. This vertex becomes a half 0, this becomes 0, 2, and this becomes a half 2. And a final transformation we'll be looking at will be a shear, which pushes the unit square over by 1 in the x direction in this case, so that it looks like that. This vertex becomes 1, 1, this becomes 2, 1, and this one remains unchanged. It is indeed rather more exotic. Now it gets even more exotic when I remind you that these transformations affect not just the outline of a square and its letter F. Now if the domain here was something more complicated, like a photograph of me, then the transformation would affect every point of the plane, and I'd end up looking like this. Well now, up to now, I've been working geometrically, but how do you go about finding an algebraic description for each linear transformation? Well, each linear transformation can be represented algebraically by a rule, which is of the form f of xy equals ax plus by cx plus dy. Now because it's a linear transformation, you'll only ever see x and y's, and not y squareds and so on. A, B, C and D will of course be numbers in general. In fact, different numbers give not only different transformations, but different types of transformations. With the shear, for instance, the rule tells you that at point xy in the domain, my I, that will map to some other point, such as this one, the image of my I and the codomain, which is ax plus by cx plus dy. Now I could calculate that point if I knew exactly what A, B, C and D were. One handy thing about linear transformations is that the origin, 0, 0, is always mapped to the origin. Now that's obvious algebraically, because when x and y are both 0, so also will f of x and y be. Now it's all very well having a function, but how do we find these A, B, C and D's? Well, that's what Alan is going to introduce us to.
Well, a very convenient way of finding these is to think in terms of matrix multiplication. Because if you write xy and ax plus by cx plus dy as column vectors, then you can represent the transformation by matrix multiplication, because A, B, C, D, the 2 by 2 matrix, times xy is equal to ax plus by cx plus dy. But how do we find these A, B, C's and D's? Well, there's a handy little trick here. Let's see what A, B, C, D does to the column vector 1, 0. And it simply multiplies it to give A plus no B's, A, and C plus no D's, C. Gives AC. And let's see what happens to 0, 1. Well, if you multiply 0, 1 by A, B, C, D, you simply get B, D. But notice, AC, the image of the 1, 0, is the first column of the matrix we're looking for, and BD, the image of the 0, 1, is the second column. So if by geometrical means you can find the images of 1, 0 and 0, 1, then you immediately have the columns of the matrix. So this reinforces the attention we gave earlier in the program to this particular pair of vectors as the basic vectors for 2 by 2 matrices. Now you'll find this trick so natural that after a while you'll be writing down transformation matrices without even thinking about what you're doing.
Well, let's hope you won't be too mindless about your mathematics. But it is an attractive and a natural shortcut. And let's try it on this first example, my rotation matrix. Now you'll remember that if you rotate about the origin through pi by 2, then this point, 1, 0, is mapped to this point, 0, 1. So the first column of the matrix is 0, 1. Now let's look at the other point, which is 0, 1. Now that rotates to negative 1, 0. So we can fill in the second column. That's negative 1, 0. And that is the matrix that determines this linear transformation, a rotation through pi by 2 about the origin. So if you want to know the rule in terms of x and y, you multiply this matrix, 0, negative 1, 1, 0, times x, y, which comes to minus y, x. And so the rule is f of xy equals minus y, x. Now you can check that on one of the other corners of my square, 1, 1. Now that ought to go to minus 1, 1. F of 1, 1 should go to minus 1, 1. And you can see that that's the case. Minus 1, 1. So that is a quarter-turn rotation anti-clockwise.
But what about rotation through some other angle? That's sort of general rotation. And we want to consider rotation through an angle theta anti-clockwise about the origin. And we need to know what happens to the two special points 1, 0 and 0, 1. So let's start with 1, 0. And let's start rotating it about the origin. Well, as it rotates, this length remains the same, 1 unit. And the angle theta is the angle in here. Now, by drawing the triangle, the right angle triangle, we can see by basic trigonometry that the vertical length here is sine theta and the horizontal cos theta. So that this particular point is the point cos theta, sine theta, the image of 1, 0. Now, remember how that actually affects our matrix, the matrix of this transformation. Well, the image of 1, 0 is simply the first column of the matrix. So we're halfway there. Well, what about the second column? Well, for that we have to find the image of 0, 1. So let's start rotating the 0, 1 now. Again, through an angle theta, and this length will remain 1. And let's consider this time this triangle. So by basic trigonometry, this length will be sine theta, this length cos theta. So the coordinates of this point here will be negative sine theta plus cos theta. And because it's the image of 0, 1, it forms the second column of the matrix. And so you can find any rotation that way. The fact that we got nice numbers for rotation through pi by 2 is just because, well, The sine and cosine of pi by 2 are nice numbers. Oh, and let me remind you again, rotations affect every point of the plane, not just these particular ones.
Well, let's have a look at my second linear transformation, which was the reflection in the y-axis. Now, the same shortcut works. Just find out what happens to 1, 0 and 0, 1. Well, here, 1, 0, this point bottom right, is mapped to negative 1, 0. So, the first column of the matrix is negative 1, 0. On the other hand, 0, 1, this point up here, stays fixed. So the second column is 0, 1. The matrix is negative 1, 0, 0, 1. Now, if you use that to multiply x and y, you get negative x, y, which means that the transformation is f of x, y equals negative x, y. And if you check its effect on 1, 1, you'll find that f of 1, 1 equals minus 1, 1. And that's just what you expected. Negative 1, 1.
Well, for a general reflection in any line through the origin, you could find a formula as well. You have to say where the axis is. So suppose the axis is inclined at an angle phi to the positive x direction. Here's the point 1, 0, and here's this point after reflection, its image. By symmetry, I think you can clearly see that this angle here between the image point and the origin will also be phi. So what we've effectively done is we've taken 1, 0 and we've rotated it through an angle of 2 phi about the origin to the point up here. And you already know the formula from earlier in the programme for a rotation through 2 phi. This point will be cos 2 phi, sine 2 phi. But we're losing track of what we're trying to do here. We're trying to find this matrix. And the matrix has, as its first column, the image of 1, 0. Cos 2 phi, sine 2 phi. And we're halfway there. Right, what about the second column? We have to find the image for the second column of the point 0, 1. And it would be reflected in our dotted line to a point down here. Now the trigonometry gets a bit difficult, so don't worry about this. But this angle here is 2 phi. And if we think of this bottom triangle, this length that I'm pointing to here will be sine 2 phi. And the vertical length here, cos 2 phi. So this point, the image of 0, 1, will be sine 2 phi minus cos 2 phi. And being the image of 0, 1, it forms the second column of our matrix. And there's our matrix for a general reflection.
Well, let's look at my third linear transformation, scalings. Well, here, 1, 0 is mapped to a half 0. So the first column of the matrix would be a half 0. 0, 1 is mapped to 0, 2. So the second column is 0, 2. Multiply the matrix by x, y, and you get so f of x, y is a half x, 2y. And you can check that 1, 1 is mapped to f1, 1, a half 2, and indeed it is. And so this matrix is a scaling of a half in the x direction and a 2 in the y direction.
So let's consider a general scaling of the form f of x equals capital AX, where the capital A is referring to the matrix A0, 0b. And by the way, we've underlined the x so that you know that it means xy, the column vector. Now, because images are going to lie on top of the originals, I want to separate the domain on the left from the codomain on the right, with f being the particular mapping. And we're going to look at these variables a and b. Let's start with the b. As b increases, so you can see the image is scaled in the y direction. If we now let a vary from 1 down the way, 1, a half, 0, and let me just stop this when a is -1, because now you see that the image is the reflection which Francesca obtained earlier on in the programme.
Finally, I'll deal with this shear. It's called an X shear. Now we go through essentially the same procedure of working that out. 1, 0 maps to 1, 0. It doesn't move at all. 0, 1 maps to 1, 1. So the matrix is 1, 1, 0, 1. Now multiply the matrix by x, y, and you get x plus y, y. And the formula is f of x, y equals x plus y, y. And when you apply that to 1, 1, 1, 1 would go to 2, 1, which is as expected.
So a general X shear is of this form, with the matrix A being of the form 1A, 0, 1. And of course, if the small a was 0, we'd simply have the identity matrix and nothing would happen. Let's now vary A, let it get larger, and as you can see, it pushes the image in the X direction. And if we stop at 1, then we get the transformation that Francesca was talking about a few moments ago. And what about the Y shear? Well, this time the matrix will still have 1s along the diagonal, but 0 in the top right and the variable in the bottom left. Let's let the variable b now vary, and as b varies in this case, you can see that the pushing is in the direction of the y-axis. There it is at b equal to 0.5, and if we continue, it pushes further and further up, and that takes us as far as b equals 1. So I hope that now gives you a good idea of what's happening when you shear in the x or the y direction.
This is a really beautiful part of mathematics, where the geometry and the algebra constantly interact and reinforce each other.
In fact, it's mathematical sheer delight.